Go ahead.
Okay, welcome everyone to HAO Colloquium. Today our speaker is Alex Pietro. It is my great pleasure to introduce Alex. Alex did his BSc and MSc at Leiden University between 2010 and 2017 and finished with an astronomy and instrumentation master's, then a PhD at Stockholm University in the solar group, which he finished in 2022. He then started a postdoc at the Leibniz Institute for Astrophysics in Potsdam, which he interrupted at the start of this year to do a 6-month postdoc in KU Leuven. Since September, he came back to Potsdam, and from March 2025, he will start on his own DFG project, which focuses on inferring magnetic fields from clear data. Today, Alex will be speaking on spectral synthesis of rotational flows in solar prominences. Yeah, Alex.
Okay, thank you. Thank you all for coming, both digitally and personally, physically. I am here to talk about the work that I've been doing the last 6 months in KU Leuven under the ERC Prominent Grant. Need to mention that. The work itself culminated in a letter, which I have the title for here. It's currently under peer review, but hopefully it comes out the next few weeks. If anyone's interested in the letter itself, I can always send a draft, so let me know. So to give a short outline of what we're going to talk about, in general, I'm going to introduce prominences. What are they? How do they work? Then I'm going to talk about rotations in prominences and sort of physics behind that. Then the prominence simulation that we've used for this work, and the Lightweaver code and the spectral synthesis that comes with it. And in the end, I show the results and discuss what I've gotten. If anybody has questions, feel free to interrupt and ask questions. I'm trying to be as clear as possible, but given all the different fields everybody's in, this is always difficult. Okay, so prominences. Prominences and filaments are the same kind of structure. So here we see a prominence on the limb. Here we see a filament on the disk. They are the same thing, and this comes down to cold, dense plasma in the solar corona, which is suspended by magnetic fields. If you look at this plot over here, with the height on the x-axis and the temperature on the y-axis and the pressure on the other y-axis, you can sort of see that for the normal solar atmosphere, the pressure goes down as we go up in height, and the temperature goes up as we go up in height. But for prominence, it's actually these kind of values that we find over here. So the temperatures are very chromospheric. They're actually similar to what you get here. And also the densities are quite chromospheric. So what we're really talking about is chromospheric plasma in the corona, which is being suspended in there. It is quite difficult to look at them because of this reason, because there's a lot going on. Either they are fully transparent or partially transparent, that you see stuff from below messing with the spectra. So it's hard to get Doppler shifts and look at these kind of, evolutions. Or they are fully opaque, and then again, it's hard to look at the Doppler shifts and the spectra because you're, again, having problems with them. So typically what people do is they look at the prominences and they try to sort of, infer what's going on, but there's a lot of discussion in that in the field. The way that they work is they are held up by magnetic fields. So what you usually have is you start with a flux rope, and this flux rope gets twisted, and then it forms a sort of nice bed for the colder material to condense in, and it prevents it from falling down further, and this is why it sort of stays up there. And as long as this flux rope is stable, the prominence itself is also stable. But of course, the flux rope itself is rooted in active regions, and these can evolve, they can move, they can rotate, and everything else. So they can change the location of the flux rope and also make it erupt or move in such a way that the material drains. So typically, it's not stable for a very long time. Below, we see some simulations of prominences. I see a little box here. I don't see that. Okay, great. We see some simulations, and you can really see that, yeah, you get this sort of twist, and then the material is hanging in it. And depending on the angle of which you're looking at it, it's either prominence, a filament, and if you look along the line of sight, you get this kind of structure, which we call a cavity. So over here, we see some observations of cavities, where here in the 171, so this is a coronal channel, we see that there's a sort of hole in the middle here, and there's material that's sort of moving in a circular fashion. In more chromospheric transition region, we see that there's a prominence, and it sort of ends where this circle starts. And if we overlay the two, we really see that we get a structure over here below the cavity center, and then we get the cavity itself. And yeah, what we're doing here, or how we believe it looks, is that we're really sort of looking along the flux rope, from one side to the other. And yeah, this shows you that looking at how, depending on how you look at the prominence, you can get very different motions and very different effects. So one thing that we are interested in this work is rotational flows in the cavities and so-called cavity tornadoes. So what you see here is a nice animation of material which seemingly is rotating. So it's sort of going around inside this this cavity over there. You can see that it looks a lot like the simulation. So this is how we think it looks and how it works. And then there's this theory by Wang et al. 2010, where they suggest that basically it's not just material that goes spirally across the flux rope, but that the flux rope itself becomes like a cylinder that's rotating, with the material just sort of sloshing around in this way. And this, so far as I know, has not been observationally proven yet. So there's discussion on if it's really a rotational motion that goes like this, or if it's sort of a corkscrew motion when material just goes further away. And yeah, this is what many people argue about. So that's always very fun. Yes.
So that one, this observation, that's like you see the sun is rotating. So the rotation apparent could be just because you're looking at different cross section.
Exactly. It could be different things.
Really,
yeah. And this is the kind of discussion that I mean, like whatever data you show, people will say, oh, it's obviously rotation or it's obviously not rotation, and it's difficult. And this is why we actually want to go into simulations where you can control what we're doing. So right
about the previous paper, is the like what is shown in A is this a shear magnetic arcade topology? Kind of is this like the two against each other? Like,
yes, I think so. Yeah.
Okay.
And then they sort of flip and they pull the material up. So here is something that people don't typically argue about, and that is if you have a flux rope that is very tight and it erupts, then of course the magnetic field lines will unwind because they're wound, and then the material starts rotating. So you get something like this video over here. So we see AIA 304 on one side and 171 on the other, and you can see that this flux rope is rising, and then at some point it erupts. And then you get this very nice sort of tornado-like rotation, where I would say here clearly it is rotating, right? But the real question is, can we actually get sustained rotation that stays for a very long time, let's say hours, more than several minutes, and that is stable, so not an eruption? Here's another one, which is a cavity. So you can see the material sort of going up in the cavity. And here, again, you can have the same kind of question. Is this material going down the tube, or is it sort of rotating in the way that I showed before in this drawing? Again, it's hard to say. Click. Okay. So there is this very good paper that came out recently by Gunnar et al. And it went over almost all the papers on rotation that I could find, and it sort of just discussed what all the problems with them are. The most common one is that you have projection effects. So I don't know how well you can see it on the screen here, but there's a little prominence there. And if you would look in the Doppler shifts of this prominence, you would see that one side is coming towards you. It's blue shifted, one side is red shifted. And this stays for a very long time. And people interpret these things historically as tornadoes because they say, okay, one part is red, one part is blue. It's a rotation. But what they actually found is if you wait a few days and make the prominence come across the disk, you see that it's this very long sort of snake. And what we probably see is that we see on one side material draining down here, and on one side material draining down there. So you get a sort of two motions that are actually going in opposite directions and are not a tornado. Another thing that was kind of unfortunate is this was for a long time one of the strongest prominence tornado detections that was there. But what they found is that actually the PSF of the ICE telescope was being a problem here. And when they took out the PSF and they sort of corrected for it, this signal, which is again red and blue, completely went away and the rotation was no longer visible. And that way they sort of went over a lot of papers and they just basically said, okay, this is not correct, this is not correct, that is not correct. I'm not mentioning the papers because I don't want to make anyone angry, but you can find that in Gunnar et al. The nice thing about simulations, though, is that there is no discussion about what's happening because we know what's happening because that's what we have programmed it to do in some way. So we stopped sort of looking at observations and we go to simulations. And we started with this very nice simulation by Liak and Keppens, 2023. And this is of a cavity that is heated from the bottom with randomized heating. And that causes it on its own, so they actually didn't need anything else apart from the randomized heating to start rotating. And this rotation keeps up, gets velocities of up to 60 kilometers per second for roughly 2.5 hours. So it's really a stable rotation that just keeps on going. The domain itself is rather small. Oh, something happened. Somebody wants to join the meeting. Okay. The domain itself is rather small, so here you can see it in megameters, 48 times 144 with a 31 kilometer resolution. For people who are more observational, that's roughly 60 by 200 arc seconds with a 0.04 arc second resolution, which is, I believe, similar to what DKIST is doing right now. So the simulations are now at the level of what we can observe from the ground with our best telescopes, if the seeing allows it. And like I said, 142 minutes of rotation. And what we see in this observation is we get rotation, we get oscillations, and we also get the cavity being formed. And also we see some coronal rain at the end. It's best shown if I actually look at the video. So here you can see the density. Here you can see the temperature, and here the velocity in the x direction. So if we play that, you can see that in the beginning you get the flux rope is rising. It starts draining the material around it into the middle of the cavity. This material condenses and you get two parts that are sort of in this cavity. So you get this rotating bit that just rotates in a very constant rate around the center. And you get this oscillating tail that sort of condenses in the bottom and oscillates away but slows down over time. So you can see that. And this oscillating tail is actually the more standard way of how a prominence forms. So this is many simulations see these kind of tails. And if you, there's the coronal ring. If you compare that to this one over here. Oh, yeah.
That velocity is the line of sight towards you, the velocity.
It's in the x direction. So it's
okay.
Along this direction. And then what you see is you get this image that we had before, and it actually looks a lot like it, right? This is what this condensing tail looks like, and we don't really see anything oscillating in here, but overall we get a very similar looking thing. Then if we simulate the AIA channels, this is also from the same paper, you can see that you get this very nice oscillating tail, which becomes very clear. It starts emitting. But the rotation is not as clear in most of them. I mean, it's this very dim little bit. I can do it again, maybe. That's sort of moving around. But you see it a bit here, but it disappears quite quickly. So what this shows is that in AIA, it's going to be hard to detect these kind of motions. I guess if it's a very dense prominence and you see a lot of material, maybe you can see these kind of rotations. But overall, it's difficult to find it this way. And for that reason, we decided to take a different approach, and that is to use the Lightweaver code. And this is a 1.5D non-LTE rated transfer code, which is based on the RH code by Han Uiterbroek, which I thought was from here, but apparently he's in NSO. But yeah, he's close. And this code basically can do non-LTE spectral synthesis. It can do partial redistribution, basically everything that you want for your spectral lines. And the only limitation is that it's really in 1.5D. We use that to synthesize the spectral lines of several elements that we were interested in, mostly lines that are observed from the ground or from space, for example, IRIS and other telescopes. And the way that it works is if you have your atmosphere, like this one over here, on the x-axis we see the height, on the y-axis we see the temperature. So here is the photosphere, here's the chromosphere, here's the corona and up. Every spectral line forms in different parts of the atmosphere. For example, here H alpha forms in the higher chromosphere, the wing forms in the lower photosphere. And depending on how the atmosphere looks, you will get different patterns in the spectral line. So this here is a example of the atmosphere, how it looks like for a very simple prominence. So here again, we get height on the x-axis, and here we get different parameters. So the number density, the temperature, and the pressure. And you can see that the density goes up for the prominence. The temperature goes down a lot, so it's this bump over here. And also the pressure goes up a bit. And what this results in is that if you synthesize the spectra, you make your light go from the top to the bottom. And in many of the lines, the optical depth will be dominated by the prominence over here and will never get to the lower atmosphere. So you won't see the photosphere. And in some of the lines, you will actually look right through it. So you'll see mostly the lower atmosphere. And in that way, we want to see, okay, what can we see in this prominence and in which lines can we see it? Here's another example. So here I used the Fal-C and the Fal-P models from the Fontelna paper, where we basically have an average atmosphere of plage and an average atmosphere of the quiet sun. So the blue one is the quiet sun, the orange one is the plage. And you can see that it's a bit hotter. So their temperature goes a bit more up. It has a higher electron density. The rest of the parameters are mostly the same. And you can see that depending on how high the spectral line forms, we get a stronger or weaker response. So, for example, in the sodium lines, we get mostly responses in the core, not so much in the wings. But in H alpha, we get a much stronger response in the core, and calcium K, which is very reactive to these kind of regions, goes strongly into emission, and also the wings go up quite strongly. And in that way, we can actually see, okay, what is going on per pixel. So there is one big issue in just plugging in a prominence spectrum into a code like Lightweaver or STIC or RH or anything like that. And that is that 1.5D does not really work well in the sense that you get radiation trapping in this area below the prominence. So to cite Jack Jenkins, who wrote this paper and solved this problem, you get a sort of space laser here because the radiation gets trapped, it gets sort of stronger and stronger, and you get a very unnatural process. And we don't want that. So the way that they solved it is they added a sort of limb darkening effect. So they curved the atmosphere so that it's no longer a plane parallel, but it's a sort of simulated sphere. And in that way, you don't get rays coming in from infinitely far to sort of heat the prominence from below. And this ray, we just calculate that. We take the radiation that comes out of it, and then we plug that in as a lower boundary. And this actually allows us to do still 1D synthesis without actually going into full 3D. So it's sort of, I call it 1.75D because it's, not quite 2D, not quite 1.5D. And this method was then packaged into a code called PromWeaver, which is basically Lightweaver with some extra functions. It was published recently also by Osborne. And it really works well with prominences. So it has all the functions to make nice uniform prominences with whatever parameters you want, or you can put in these more complicated atmospheres that we have done over here. And that way you can sort of get across these problems. So the way that I've been working on this prominence is you can integrate the atmosphere along two ways. So if you integrate it from top to bottom, you get filament. And if you integrate it from left to right or right to left, you get a prominence. And then what you do is for every ray, you get one spectrum. So you can get a simulated slit that goes sort of up and down or along the x-axis. And the difficulty of this is that depending on how complicated the atmosphere is, it can take a while to actually synthesize these spectra, from a few seconds to a minute or something. And the more columns you have, of course, the more time it will take. So here you can see an animation of how this sort of looks. So we are moving the slits or moving the column along the interesting regions. And you can see that here where we get this this rotating bit, we get a little Doppler shift. So you actually see that the wing is absorbing and it's sort of moving to that way. While in this tail, because you have material that's moving left and right, you get a sort of general broadening and deepening. So this works quite well.
Filament way.
This is the filament, yes, filament mode. Then if we do it for the whole window, we get these kind of images. So how you should interpret this is every image has the x-axis here. So this is just the spatial direction. And here we see the wavelength axis. And every column is basically one spectrum. So it's kind of like this blue line is an example spectrum of the quiet background outside of the prominence. And then we get calcium 8542, H alpha, calcium K, magnesium K, Lyman alpha, Lyman beta. We ignored calcium H and magnesium H because they are very similar to the K variants, so we just didn't want to spend more time computing those. But if you look at the results, you can see that here we get a sort of deeper. Some people talking. Here we get a sort of deepening in the profile, so we can see this sort of oscillating tail, but we don't see any Doppler shifted material, so the rotation is not really visible. In calcium K, it's very similar, but then if you look in magnesium, I hope that's clear on the screen, you can see that there's this strongly Doppler shifted component over there, which is actually this rotating component that we saw before. And then in Lyman alpha and beta, we can see that also these components are quite prominent. So that is promising in one direction because we can see it, but we can't see it very well in the lines that people usually use, which is H alpha. Then we can do the same in prominence mode. If we move the line up instead of left, right, we then move across this tail and we're going to see some general emission. Oh, it just does it once. Do it again. We just get some general emission in the center, and then when we get to the rotational part, we get another blip, which is higher redshifted due to the rotation. And then if we, there we go, all the doors are closed now. Then if we repeat the same process for all the columns, then, or sorry, all the rows, then we get this image. And what I need to point out is that it's now flipped as opposed to the last image. So the Z-axis over here is this axis. And here we have the wavelength now, because we're looking at rows and columns. In the calcium 8542, you can see that there's just no signature whatsoever of this prominence. In H alpha, we do see the oscillating tail, but we don't really see any, again, rotation. In calcium K, interestingly enough, we do see a rotation, which is quite strongly Doppler shifted. And then in magnesium, it gets stronger. And in Lyman alpha and beta, it gets also a lot stronger. So we get, better results the higher we look in the atmosphere. Which makes sense because, of course, the higher we are forming, the more optical depth it catches for the rotational part.
Kind of a little bit tricky to see here, but so Lyman alpha, for instance, higher up in the prominence looks like it's double peaked, right? Like
here,
Lyman alpha in
yeah.
the middle. But magnesium K looks like it's probably single peaked. Like the spectral profile. I mean, if I'm along the wavelength, is that what we see in observations?
That's a good question. I mean, in Lyman alpha, we don't really have a good spectrograph that does this. So this is, it could be real, it could be completely fake. We need a few 100 million to send something up to space and then check. So if you guys have that.
US, Chinese.
Yeah, but they only have imaging.
Oh, the Lyman alpha?
Yes, it's only imaging, yes.
The H alpha.
Yeah, the ASOS satellite, yeah.
Okay.
Yeah. Very unfortunate, but no spectra yet. And in Iris, this is something we want to check if this actually is going to look like this. And I'll get to that later for observing strategies, because there are some that will have to be done and they're non-standard. So I don't think there's going to be anything in the archive, but yeah, we haven't checked deeply yet. One thing that, of course, so we did all of these simulations, so we did these very nice spectra for the snapshots, but then, of course, rotation requires a time component. You can't just look at one snapshot and say we see rotation. So what we want is to actually do the whole time series, the whole 140 minutes. But the problem is that it's very, very computationally expensive. And on my MacBook, doing one of these maps that I showed you before took around 100 hours. Using the whole MacBook, I couldn't use it for anything else. The mouse wouldn't even move anymore. It's just, you lose your computer for 3 days. And that's fine for, one, but if you have 1,000 snapshots, because that's how many we had in the time series, that's a bit too long. So what we then decided to do is we sort of made a sparse map of the simulation. So we took every 16th column or every 16th row in the simulation. And we took 16 because that was a number that the rows and the columns were divisible by without any decimals. And it ended up in a roughly 100 rows and 100 columns. And then we also synthesize every 10th snapshot instead of every one. So then we reduce everything by a lot. And we need to get only around 600 hours to now simulate the whole time series. And we used some other computers. I didn't really have access to a big cluster, but I had access to some smaller clusters with some of the collaborators. So this was in the end doable within roughly a month or so, which was very nice. Parallelizing it was troublesome. We tried to make a sort of parallelizing library to package that into the code and publish it for everyone to use, but this did not work yet. I'm not sure if this will be fixable anytime soon. So right now, if anybody's interested in this kind of work, the best way that I found to do it is with what I call the poor man's parallelization, where you just start multiple terminals and you say the first 10 rows go here, the second 10 rows go there, and then you take another computer and just continue it that way. This works, but everything beyond that needs more work. Anyway, what we then did is we repeated it for all these time steps that we had, and I made these nice animations that I have here. So before I started, here you have the line of sight velocity. Here you have the density. Here you have the temperature. This is for the filament view. Then we have calcium, H alpha, calcium K, magnesium, Lyman alpha, and Lyman beta. And what you then see if I started is when the flux rope actually goes up and starts rotating, you see that you get this very nice rotational pattern, specifically in magnesium, where you really see a strong sort of up and down motion, but also in the other lines, you do see the Doppler shift. So let me just start it again. In H alpha, for example, you can see that there's some movement going on, but it's very faint. Here you can see it a little bit jumping up and down. Then you see it also in calcium and in Lyman alpha. What's also interesting is that it sort of blends together with the condensing tail. So just because of the difference in velocities, you see that there's some difference in the Doppler shift, but if this thing would be rotating slower, you would probably not see the difference between them. So in the end, I would say that magnesium is the best line to look at because you get very strong Doppler shift excursions just purely due to the wavelength. So I'll just show that again, and it's sort of jumping out of the window even in some instances, while the oscillating tail is really nicely confined to the middle part. And here you can see that it is emission, single peaked emission. Then I did the same for the prominence. So just remember it's flipped. And as the prominence goes up, you can see that there's a little bit of emissions visible in H alpha, but not as much. And you see that there's more in the lines that are going up. And this is the coronal rain coming down. That's also kind of cool to see how that fills the entire image in the lower spectra. But in general, you can see that these oscillating tails are very clearly visible. I also like how you can sort of see that they're swashing about. And the rotation gets, very well visible again in magnesium. In Lyman alpha and beta, you can see it kind of well, and in calcium, but in H alpha, it is difficult. And in a way, that is a nice result, because what that shows is that the people that have been looking for these kind of structures mostly look in H alpha, and this could be an explanation of why they don't see them. So it's sort of not too much going against the established literature. On the other hand, this is a 2D simulation, so the densities are not fully realistic, because if you work at a 3D flux rope, you will get better material being moved up and down. So this is something that we want to do in the future, where we use a fully 3D rotating flux rope, and Valeria is actually working on that, so that's something that will come out hopefully in the next few months. But based on these results here, I would say that H alpha is just not a good metric or a good way to look at these kind of rotations. Okay, so with that, I come to my conclusions, where I'd like to say, yeah, PromWeaver is a very good tool for studying prominences and their dynamics. The rotation is potentially too weak to detect in H alpha, but it has very strong signatures in both magnesium and Lyman alpha. This means that we should really try to hunt for these things in iris. And the way that I would do that is by doing sit and stare observations in prominences and not rasters, because if you have a raster, everything evolves, everything moves, and it becomes difficult. But in a sit and stare, you get something that I had here, because these are in principle sit and stare observations that we're looking at, that we simulated. And that's why I don't think they exist, because I've not heard of people doing sit and stares on prominences in general. I don't think it's a very common strategy. So that's something I'd like to talk about with the iris people to try. And the other thing is that we really need a Lyman alpha spectrograph to be made. And yeah, if that can be done in China, that's great. If you guys need a project, that's also great. But that's my tip for, fill the gap, please. And that's the talk. So thank you.
Thank you. So now is open for questions. Anyone, you can unmute and ask your question. Or anyone here in the room? Not yes.
I have one question. It's more about the simulation. What physical process causes this rotation in that simulation?
Yeah, so this is described in a lot of detail in the paper. So I will wait. So I would refer you to that for all the nitty-gritties. But basically, they added some randomized heating at the bottom, which was the only thing that they really changed. So they took a standard flux rope, which without the heating just becomes this cavity. And with the randomized heating, it started rotating on its own. So it's it's a surprisingly physically accurate way of doing it, I would say. They didn't need to cheat it or force it or give it anything to do that. Yeah.
Is the entire boundary changing in terms of heating, or is it like parts of the boundary?
I think it's just a few places get some different parts in the heating, but I've not done the simulation, so I'm not an expert on that part. So I would refer you to the author. Yeah.
So
And this simulation is 2D, right?
Yes.
So in that sense, if it's 3D and this flux rope is somewhere rooted, then that likely would prevent the rotation at a very strong level, I would assume, at some point.
Yeah, so this sort of the discussion, because what in principle the magnetic field, I don't have it plotted here, is not rotating. It's really the material that's sort of corkscrewing through it.
Okay.
And that, this is one of the discussions that people have because if it would be the field lines, then at some point it would twist too much and it would break. But if the field lines are sort of stable, then the material can, do what it wants. And I think that's the big definitional debate that we're having. Is the rotation that the whole thing is rotating, or just the material in there? And in this case, we're really talking about the material.
Okay.
Yeah.
can you run that again?
Yeah, of course.
So so there is a constant heating at the base
Mm-hmm.
to cause the Crum's condensation to form, right? There is, but then in addition to that, you add these random points.
So you can see it's sort of you can kind of see it here, I guess, that it's moving around a bit. You can see that the brightness changes a little bit. So it's not even a very strong heating term.
Left is the temperature.
Yeah.
So because it's 2D, it's effectively a whole length is being heated.
Yes. Yeah, and it's 2.5D, so it also has some there's some communication with the velocities, I think, in the tube, but there's no the boundary condition is sort of doing that. But yeah, I would really recommend talking to the person who made it, because I have not worked with AMR back myself. So yeah, it's about where my knowledge stops. Yeah.
Have you considered to look at helium-10 at 830?
I have, but the problem is that this code cannot synthesize that. Then you would need to use Hazel or one of these kind of codes. And in principle, that is doable. So we could just take what we have now and then repeat it there. But just because I was using this code, it was sort of out of the scope, let's say.
Yeah, from my observational experience, I would suspect that helium-10 830 would be a good tracer.
Okay. Yeah, I know the people who work with the line a lot, so this might be something to suggest to them to just repeat this work with 10 830. I think the only thing that they would have to build in is this boundary condition that I talked about, this one. And after that, I think it's just a simple running and making the prominence. Yeah, no, but that's a good suggestion. Thank you.
Anyone online? Oh,
Yeah.
Robert.
I was wondering, in terms of the observations, do you see like systematic rotations? Like when you just look at the rotations, like depending on like hemisphere, solar cycle, etc.
What you mean outside of prominences in general, or?
No, like from in terms of the prominences, like if you observe them on the east or west limb or on the individual hemispheres, do you always observe the same rotational pattern? Does this follow the magnetic structure, or?
So I don't have the image of it, but let's see this one. There is a video of like the full disk, and there's actually another one on the northern limb, and they rotate in the opposite directions. If that's what you're asking, so they
Yeah, right. Yeah.
they're opposite in that direction, or in that sense. But this whole rotational thing, it is difficult, like just because, seeing and the projection effects and everything else. Observationally, I don't think anybody agrees on if we've seen rotation or not.
Okay.
Anyone online?
So I have a
Yeah, please.
observation in UCOMP, it's our telescope. HAO has see line of sight flows, like bullseye
Mm-hmm.
shape, concentric rings of flows towards you, away from you.
Mm-hmm. So a
And,
bit like this, or
it's line of sight, so it's like going to,
uh-huh.
this is just your parent.
Yeah, okay, so it's like a spiral coming.
Yeah, so it's like, no, actually, it's like if in the center, the one direction, and then there's concentric rings of flows towards you, away from you.
Oh, okay, okay.
So it's like flows along flux surfaces,
Mm-hmm.
one way or the other. It's just there are other patterns, but this is one of the patterns.
Mm-hmm.
So in this, I guess you don't see that in this simulation. You don't have any systematic flows along the flux
No,
road.
but it is a 2D simulation, so that's of course
Okay, yeah.
we
okay.
don't know what's
Yeah,
going on in this.
you
Yeah,
won't see that.
yeah. But I think in the 3D ones that's there.
Okay, so if it's 3D, then yeah, we try to do that, but we can't get persistent timescales.
So this one here is.
Try to see that
Mhm.
we do see prominence oscillation, along the field line
Uh-huh.
oscillation. So it does show, but it's very hard to create this concentric ring.
Yeah, I can imagine. Yeah, but this is the one that they're working on in Belgium now, and it is so the 3D structure is sort of set and it is behaving in the way that they want it to behave, but it's not complete. It's not ready yet, so we haven't done any calculations. And of course, if you want to synthesize the whole thing, that's also going to be very expensive because then we get a new dimension of
Yes.
of rays that we can play with.
Other questions and from online? Anyone? Okay, I don't see anyone raising hand online. So let's thank our speaker again for giving nice talk.
Like the-